The activation function in a neural network acts as a gatekeeper, determining whether a neuron should activate or remain inactive based on its input. It takes the input, a weighted sum of signals from the previous layer, and applies a nonlinear transformation. This function makes a decision similar to a gate, either allowing information to pass through or blocking it. Activation functions introduce nonlinear properties to the network, allowing it to learn complex patterns. The neuron is represented by a circle. The input arrows show the signals coming into the neuron. We then visualize the weighted sum of these inputs. Next, the sum is processed through an activation function, indicated by an arrow. When using the ReLU activation function, we can see the ReLU equation and understand how the neuron fires. Finally, if the neuron fires, the output signal is generated and sent out. The ReLU graph shows how the ReLU activation function works. It's a piecewise function that outputs 0 for any negative input and passes positive inputs as they are. This helps the neural network by allowing only the most significant positive signals to pass through, effectively ignoring negative noise. The graph has a flat line at 0 for all negative values and a straight line with a slope of 1 for positive values, making it simple yet powerful for deep learning tasks. How ReLU is used in recognizing handwritten digits. Layer-by-layer processing. When a neural network processes an image of a handwritten digit, each layer in the network applies the ReLU function to the output of the previous layer. This process helps in preserving positive signals, which are important features, and ignoring the negative ones. When building a neural network to recognize handwritten digits, each neuron in the network focuses on processing a small part of the image, such as detecting edges or shapes. It sums up the input signals it receives, and then the activation function determines if the neuron should fire and transmit its signal to the next layer. For example, if you use the ReLU activation function, only strong signals, positive numbers, are passed on, while weaker signals, negative numbers, are ignored. This selective process allows the network to concentrate on the most critical features, like the curve of a 9, enabling it to accurately classify the digit. Ever wondered how your email filters out spam? Behind the scenes, there's a powerful tool at work: neural networks. Imagine you're developing a neural network to predict whether an email is spam or not. The network processes various features, like the presence of certain words or the frequency of links. Each neuron in the network evaluates these features and sums them up. But how does this sum turn into a decision? Here's where the activation function comes in. Take the sigmoid function, for example. It transforms the neuron's sum into a probability score between 0 and 1. Input features. These are the features extracted from an email, such as the presence of certain words, links, or other indicators that might suggest the email is spam. Weights. Each feature is associated with a weight. These weights are learned by the neural network during training and represent how important each feature is in making the spam classification. Weighted sum. The weighted sum is calculated by multiplying each feature by its corresponding weight and then summing these products. This sum gives us a raw score before any activation function is applied. Sigmoid output. The sigmoid function is then applied to this weighted sum. The sigmoid function converts the raw score into a probability between 0 and 1, indicating how likely the email is to be spam. Spam classification. Finally, based on the sigmoid output, the email is classified as either spam or not spam. If the output is closer to 1, the email is more likely to be spam. If it's closer to 0, it's more likely not spam. Here we are visualizing how a neural network processes an email to determine if it's spam. The animation begins by highlighting key features of the email, such as specific words and links. These features are then fed into the network's input layer. As the inputs pass through the hidden layer, more complex processing takes place. Finally, the data reaches the output layer, where a sigmoid activation function converts the combined input into a probability score between 0 and 1. This score determines whether the email is classified as spam or not. The entire animation visually breaks down this complex process, making it easier to understand how the network arrives at its decision. Imagine a self-driving car. cruising through a bustling city, seamlessly adjusting its speed based on the environment. But how does the car make these decisions? Today, we'll explore one crucial part of that process, the Tanh activation function, and why it's essential for safe and efficient driving. In a self-driving car, the neural network processes various inputs like the car's speed, the distance to obstacles, and the curvature of the road. Each of these inputs is multiplied by a weight, a value that reflects its importance. For example, the distance to the nearest obstacle has a higher weight because avoiding collisions is critical. These weighted inputs are then summed up, creating a single value. But how does the network decide what to do with this value? That's where the activation function comes in. Now we're focusing on the Tanh activation function. The Tanh activation function takes the summed weights and transforms it into a range between -1 and 1. This might seem simple, but it allows the network to make more nuanced decisions. Unlike other functions that only output positive values, Tanh provides a balanced approach, handling both positive and negative inputs effectively. This property makes Tanh particularly useful in situations where we need the model to handle both positive and negative inputs, as it centers the output around 0. So, why is this important for a self-driving car? Let's break it down. If the Tanh output is close to 1, the network might decide that the car should accelerate. On the other hand, if the output is near -1, it could indicate that braking is necessary. And if it's close to 0, the car might maintain its current speed. In the fast-paced world of stock trading, every slight movement in price can mean the difference between profit and loss. But how can a neural network help predict these movements? The key lies in the activation function used by each neuron in the network. Today, we're diving into Leaky ReLU, a powerful tool in predicting stock prices. Imagine you're building a neural network to predict stock prices. The inputs to the network include past prices, trading volumes, and economic indicators. Each neuron in the network processes these inputs by applying weights and summing them up. Unlike the standard ReLU, which outputs 0 for any negative input, Leaky ReLU allows a small non-zero output for negative inputs. This seemingly small change has a big impact. It helps prevent neurons from becoming inactive during training, a problem known as the dying ReLU problem. For instance, if the network detects a slight negative trend in stock prices, standard ReLU might ignore it completely. But with Leaky ReLU, even this small dip is passed through, keeping that information within the network's decision-making process. With this enhanced capability, the neural network becomes a more powerful tool for investors, providing insights that are both deeper and more accurate. Whether it's spotting a minor downturn or a major market shift, Leaky ReLU helps ensure that nothing is overlooked.